Yeah, hello everybody and welcome to today's event, case studies on propulsion. And of course, may the 4th be with you, because we are in the space industry after all. Yeah, thank you very much for giving us, your time and attention today on this lovely Wednesday. There's, in the world today, there's approximately 3 billion important things going on. Actually, I counted earlier. And there's lots happening in the space industry as well. So we really appreciate that you're spending time with us. And in the industry, indeed, the topic of propulsion is a very interesting one, and one that's gaining increasing importance. So today we want to share with you, give you a closer look at what is really possible with thrusters and what benefits they can bring to space missions today. So we'll get to the first presentation shortly. We just started a few minutes over, so we're looking pretty good. But firstly, I just wanted to share a few important things. Unfortunately, we're sorry, but our friends at Pale Blue and Nano Avionics have had to pull out of today's event due to some competing priorities. But they both hope to share their own insights at a future session with us. So yeah, apologies for that. This means that we will have a little bit of time for a couple of extra questions. So the way we would like to run it is to do each presentation, followed by, after each presentation, we'll do a couple of questions and I will moderate those. But throughout the entire webinar today, please do use the Q&A function in Zoom to ask questions of any of the participants, any of the panelists, or general questions at any time. Obviously, when they're given their presentation, they won't be able to answer, but they will be able to answer before and after that. So please do use that as much as possible. We find this a great way of people being able to ask really considered questions, and you don't have to rely on your voice, not being heard and your question not being got to. So it would be great if you can ask anything that you're interested in on the topics discussed today. Links will be shared in the chat function as well, so and also feel free to use the chat function to talk to other audience members as opposed to talking to the panelists, which is what the Q&A function will be useful. And following the event, we will work to get you a version of the slide decks shared today, and the webinar is recorded, so we'll get access to that video for you, which you can share with anybody who was unable to make it today. So I think that's everything that we would need. If you have any other questions for us as the host, please do ask them in the chat function, and we will we'll respond to you when we can. So I hope you enjoyed today's event, and I would like to hand over to our first speaker today, which is Exotrail.
Hi, hello everyone. Let me share the screen. So I think you can see it. So hello everyone, thanks for being here today. I'm Mayer Girard. I'm the propulsion product manager at Exotrail. And today I will present you my presentation in 3 parts. So the first one will be a short introductory of Exotrail, who we are, what we do. And then I will focus on our in-orbit demonstration missions that we launched in 2020. And finally, I will show you a small use case that our propulsion system allows. So let's go directly into the presentation. So at Exotrail, we are an end-to-end mobility provider. We do not only provide propulsion systems, but we want to provide solutions for all mobility needs in space. So for this, we have several products. So the first one, allowing us to define and to better understand the needs of mobility in space, is our ExoOps mission design software, which is a mission design analysis tool, basically. And thanks to this and the quite well understanding of the mission, we're able to provide 2 kind of solutions. The first one, which is an onboard propulsion system that I will depict a bit later, and the second one, which is our orbital transfer vehicles called Spacevan. And finally, we are also able to operate our solution directly thanks to our operation system called ExoOps Operation. So speaking about propulsion systems, at Exotrail, we're developing Hall effect thrusters, Hall effect propulsion systems. So I won't dive into how a Hall effect works, but the thing I want you to have in mind is that Hall effect thrusters have the highest thrust to power ratio in all electric propulsion systems combined. So, and this with a good efficiency as well. So basically, it's a very good compromise between standard chemical propulsion systems and with low ISP and high thrust, and other electric propulsion systems with low thrust and high ISP. So we have several products at Exotrail. We have the ExoMG Nano, which is the first one we developed, and this is also the one that is in space through the in-orbit demonstration mission. So it's a 60-watt class propulsion system delivering around 2.5 millinewton of thrust. So it's quite suitable for small delta V needs or CubeSats. And then we have also developed the ExoMG Micro, which is a 150 watts class propulsion system, delivering up to 7 millinewton of thrust. And depending on your needs, depending on the mission requirements, delta V, lifetime, etc., we're able to clusterize our propulsion systems and to propose several clusterization, like a cluster of 2 micro, which is basically a duplication of all subsystems except the tank that we can communalize between the systems. But otherwise, there are exactly the same systems as the micro. And we can go up to 4 or even more clusters, allowing us to have up to 28 millinewton of thrust. So now we'll go directly into the in-orbit demonstration mission. So our IOD was launched in 2020, as I mentioned. And for this, we adopted a develop and fly philosophy. So this means that we design, qualify, and delivered our propulsion system in quite a challenging time, so in only 10 months. And we performed the full coupling test integrated with the nano avionics platform. We threw within a nano avionics platform, a 6U. And also another important thing we have done through this in-orbit demonstration mission are the validation of range safety topics and ground and air transportation. Because at Exotrail, we're delivering our system fully fueled with gaseous xenon. So we had to validate these topics to make sure that we can ship our propulsion systems everywhere we want. Speaking about specification, so on the left, you can see some specification we had for the IOD. So we had a 55 watts power requirement with a minimum thrust of 1.8 millinewton with 700 seconds. And all of this within a 2U plus tunacan volume. So this was for the IOD. Nowadays, we have more, we have continuously improved our product, so we can achieve the same level of total impulse within only 1U plus the tunacan. So we achieved this, and we also have better performances, as I will show you right after. So in terms of propulsion system, we have 4 building blocks, and we managed to monitor several parameters to examine the health of the system during this mission. So basically, we put several thermal sensors. We put also pressure transducers to evaluate how the behavior of our propulsion system in orbit. So we have 4 main building blocks. I won't go too much into details on this, but basically we have the thruster head, which is here for the IOD, which was the THT Nano, so 60 watt class Hall effect thruster. We also have the xenon management systems, which is basically used to control the mass flow rate for the propulsion system. We have the TCU, which is an OBC. So this is the onboard computer of the propulsion system, which delivers telecommand telemetries, which also delivers the right level of power for every element of our propulsion system. This is also the only interface we have with the spacecraft. We limited the interface with the spacecraft, electrical interface, of course, to this block. And finally, we have the tank assembly, which is here to store the xenon during lifetime. So in terms of timeline, just to show you a bit what was done before the launch. So we kicked off the project in November 2018, and as I mentioned, we were quite quick in the designing, qualification, and delivering phases, since we were able to deliver something, and when I mean something, I mean a full propulsion system, of course, in September 2019 for integration on the spacecraft. During this integration, we also successfully went through acceptance tests at satellite level and range safety certification. And this was just before sending our propulsion system and the spacecraft itself toward India for the PSLV launch. So the first launch was expected in November 2019. However, due to the context, COVID and etc., we were stored during 1 year in India, and the launch was only able to be done in November 2020, so 1 year after. However, this was actually quite good opportunity for us to test the leak rate and to see if we had any problem during this storage. And yes, we haven't detected any leak rate during this slot, so that was quite a good news for everyone, I think. And yes, we just leak-proof our propulsion system thanks to this. So after the launch and platform layup, we were able to have the hand on the propulsion system and on the spacecraft for 1 month to firstly do commissioning, etc. Before letting this to another payload that was also embarked in the spacecraft. And then in February 2021, we were able to get back to the propulsion system and to test it, to perform several maneuvers, characterization, and so on. So during the commissioning phase, as I mentioned, we mainly perform checks, so communication checks like telemetries, telecommands, validation, thanks to our ExoOps operation software. So we also validated our operation software thanks to this IOD, not only the propulsion system. But we also perform 3D checks, so mass flow regulation, xenon mass estimation, and thermal conditioning. And one thing that was important here is that we were able to have the same level of performance and the same set points either with gaseous xenon or liquid xenon. So this means that thanks to our IOD, we know that our propulsion system can work either with gaseous or liquid xenon. So we do not require to have any thermal conditioning of our tanks in orbit while off. So the propulsion system doesn't need any of this. And finally, during this month or so, we made several checks like thruster head checks, cathode conditioning, anode polarization, thermal conditioning of the thruster head, etc. Then during the 3 months operation that we had starting in February 2021, we were able to perform several maneuvers, several characterization of our propulsion system, in-orbit characterization, and we were quite glad because we developed an average thrust of 2.6 millinewton at 60 watts, where the specification was more around 1.8 millinewton at 55 watts. Sorry. So we had quite good results in space, higher than expected based on ground tests. So that was quite interesting for us to get this feedback. And also during this period, we performed like a 10-kilometer orbit raising to test our propulsion system. So I will take the four last minutes to speak about one use case that our propulsion system can allow. So I would like to speak about constellation deployment. If we consider a typical constellation of 24 spacecraft of 20 kilograms each, and we want to deploy them on 6 planes with 30 degrees between each planes at SSO 550 kilometers, we can typically have two different strategies. So one of them consists in having dedicated launchers. So we want to have 6 planes, so 4 spacecraft per planes. And so we would take 6 launchers to get to the final constellation operationality. But this solution is quite costly, since we evaluated it at around $800,000 per spacecraft, which will represent a very huge cost just for launch deployment. And on the other hand, we have the second strategy, which is to use rideshares and to perform run phasing, so plane changing directly after launch, the launcher deployments. So in that case, this solution is quite cheaper, like almost 8 times cheaper than the dedicated launch solution. And I will show you next slide that it will take almost I won't say the same amount of time, but it's a reasonable amount of time. But so in that case, in the rideshare typical launch offer, we would require to have a propulsion system that is allowing deployment of spacecrafts. So to have 30 degrees of run and minus 30 degrees of run on several spacecraft. So basically, the strategy will be to have 12 spacecraft in one rideshare launch, and to have 4 of them staying on the launcher plane, to have 4 of them going at plus 30 and 4 of them going at minus 30 degrees. So in that case, we will have the 3 planes. And so if we go into these slides, we compare using our propulsion system, so ExoNG, to another propulsion system, like a low thrust electric propulsion system, with almost the same power level requirements here. And what I want to highlight here on this slide is that with the low thrust electric propulsion system, it can take up to 9 months, minimum 9 months, I would say, to perform the 30 degrees of run, where using our propulsion system, it will take only 5 months to perform it. So this is quite huge in terms of time difference. And if we compare, if we go directly here, I don't know if you can see my mouse, but if you go directly on this scheme, here I compare the dedicated launchers time frame, the ExoNG time frame, and low thrust electric propulsion time frame. So using dedicated launchers and considering 1 month of electric orbit phasing, it will take around 7 months to have the full operational capability of the constellation. Whereas using rideshare and ExoNG, so considering 1 launch every 4 months, which is typically the SpaceX offer we have today, we can see that we will be able to reach the full operational capability of the constellation in 9 months. But using the low thrust electric propulsion system, it will take up to 13 months to have the full operational capabilities. So to conclude on this part, and based on our assumption, what we can see here is that using rideshare allows you to drastically reduce the cost of launch, while if equipped with the ExoNG, so it won't make the full operational capability of your constellation too long. So it will take, there is only a 2 month difference between full operational capability on dedicated launchers rather than using rideshare with ExoNG. And also what we can see here is that using low thrust electric propulsion system double the time to get to the final orbits, which is quite expensive and which costs a lot to spacecraft manufacturers. So this concludes my presentation. Thank you everyone.
Great, thank you very much, Mel. That was really interesting. Thank you. It's very illustrative, I think, of the challenges that the companies face in space. You know, you've had to deal with those delays, and yeah, it was great to see the technical information about constellation deployment, rideshare versus dedicated launch. So thank you. So we've got a couple of questions for you, as I mentioned. So firstly, Jeff Crookin asks, was there any special type of storage facility needed during the year of storage, when your launch mission was delayed?
So no, there were not any specific regulation. I mean, it's a spacecraft storage. So for me, I wasn't here during the in-orbit demonstration mission, but for me, it was stored directly within the PSLV launcher.
Okay, great, thank you. Another question from Joshua. I don't know whether this is correct, but Joshua says that 70% of the world's xenon supply comes from Ukraine. Are you currently experiencing any propellant supply chain issues? Let's keep it non-political as well.
No, sure. But no, we do not experience this, since we also have a lot of provider in Europe. So our providers are mainly in Europe, so we do not see any difficulties on that.
Okay, great, thank you. And finally, just a quick question from me, and there are some others in the chat. I think if you could move those over to the Q&A, they'll be able to be answered after the presentation. But
yes.
You've compared the situation with rideshare versus dedicated launch there.
Yes.
From your perspective as the supplier of the thruster system, are your integration and testing processes different if you are, going to be on a rideshare versus dedicated launch?
No, from a propulsion perspective, we do not see any differences between providing thruster for a rideshare or for dedicated launchers. I mean, it depends on mechanical environments that we see, but our qualification covers all of this environments, so we do not expect any difference.
Okay, fantastic. Thank you. Well, yeah, if there are any further questions, please do ask them in the Q&A, and they can be answered there. But thank you very much for the first presentation there.
There we go. So yes, my name is Lou. I'm the product manager for the Impulsion Micro, which is one of the products that we sell at Impulsion. So I've been trying to focus this presentation a lot on lesson learned about customers selecting propulsion systems and what we see when they come to us, and what could maybe help people get better prepared to select a propulsion system in the future.
Lou, I'm sorry, your screen isn't sharing just yet.
Let me, because I didn't click the share button. There you go.
There we go. Thank you.
Sorry about that. Yes. So first, quick overview of Impulsion a little bit. So we manufacture a small all-in-one electric propulsion system based on the FIP technology. So far, we have delivered about 250 thrusters to more than 10 different constellations and individual IOD demonstration. We have about 100 thrusters in space, and I think we are breaking 50 spacecraft next month, right about it. So those thrusters are sold well, pretty much everywhere in the world, from US, Canada to Asia, and of course, all over Europe too. So very different types of customers, from universities, research project, to much bigger, more, let's say, professional or traditional space customers. And those customers come to us for our small propulsion systems. So the main one that we have been flying so far is the Impulsion Nano, which is a 1U system based on the CubeSat form factor, and which is about a 40-watt unit, 350 micronewton. And this is the one we have been flying the most so far. and seeing the maturation of the market and like a little bit the, let's say, professionalization of new space. We have also spun up this thruster into the Nano R3, which features more robust electronics, most notably in terms of radiation tolerance, reliability, and closer to some of the traditional space requirements instead of the pure COTS approach, and which departs a little bit from the CubeSat form factor that is not necessarily the one that people actually want in the end. And we have also a more powerful thruster, which is the Micro R3, which is a panel-mounted system, which developed about 1 million at 100 watts. And that thruster also has been flying since last year. So we have, yeah, as I said, about nearly 50 spacecraft in orbit, doing all sorts of different missions and in all sorts of different environments. We have things in low inclination orbit, things in some synchronous orbits, low and high some synchronous orbit, and even all the way up to GEO in some spacecraft. So we see a very different use cases for thrusters. A small example here. This is, for example, one of the constellation phasing we have seen from one of our customers with our Nano product. So you see at the beginning the two spacecraft on the similar orbit there during commissioning, where they follow along the same track, and then they started the orbit raising on the first one to reach their operational altitude, and then after the delay, phasing delay to get the right separation, you see the orbit raising for the second spacecraft. And then you have formation control, then formation flying control, which is something we see a lot in our customers, where small bumps corresponding to the thruster turning on every few days to maintain separation and phase. All right, so when we see people coming to us in terms of RFI and propulsion requirements, often we see that people there is a different way of speaking between the system engineer who is looking at the mission phase and also the propulsion provider. We're looking at, well, the propulsion performances. And often it's not always easy for us to answer direct RFIs because we don't have the information or the full things, all the requirements that we need to be able to answer questions directly. So I've been trying to put together there like a little bit of a face-to-face between what is important for the operator and what is important when you write propulsion spec for your propulsion providers. So as Maël said previously, one of the things interesting is the transition time, right? How fast can you get into operational orbit, and this is directly related to the thrust and thrust to power, of course. We see also often people asking about mission lifetime, which as a propulsion subsystem provider is not always easy to answer because we do not necessarily know the environment that the spacecraft will be in. So it's often better to formulate it as reliability requirements, radiation hardness requirements, and also having more details in what is the operational scheme that you want to do, because the reliability and the lifetime reliability will be different, of course, if you fire every day compared to if you leave the thruster off for 2 years and then only fire for the orbit at the end of mission. We see often people also focus on delta V and then trying to focus on ISP. And for me, at least in terms of small spacecraft, it is often a mistake to focus only on ISP because the propellant mass on a small spacecraft will almost always be negligible compared to, or very small compared to the spacecraft mass. And those requirements are often better expressed in terms of total impulse or system impulse density, or that kind of numbers, where you actually see if you can fit into your volume constrained spacecraft the total impulse that you need, and also if the system has the lifetime to be able to deliver that total impulse, which is always very important. And then something that is not always very well expressed into specification is all the AOCS aspect. Because different technologies will have different thrust vector alignment or precision, possibility of doing thrust vector control. So for example, at Impulsion, we have one thruster that can do thrust vector control in a non-mechanical way, which can be interesting for some applications, especially higher up than LEO. And then also sometimes people want to have the possibility to vary the thrust, to operate at high thrust and then low thrust, depending on the power they have available or the mission phase that they are in. And then you have things that are more specific to electric propulsion, if you look at it. So one of the dirty secret of electric propulsion for small sat is that ISP is not actually very relevant. What you are really looking for is the total impulse, because everybody is selling off-the-shelf thrusters, mostly off-the-shelf thrusters for CubeSat and small sat, where you have one or two, maximum maybe 3 tank size, and you will be filling the tanks as much as possible. So what you care about is how much impulse you can have in the system and not so much the ISP that the system is operating at. Power is one of the bigger limitation factor for EP. Unless you have radar satellites where there is a lot of it, most of the time you will be power limited in terms of utilization of your propulsion system. So that's always something very important to pay attention to, and that will really drive your operational philosophy in terms of how often you turn your propulsion system. Do you keep it in hot standby to be ready to fire, or do you turn it off completely? That kind of thing. Thrust accuracy, that's also a very important thing where we often see people over-specifying what thrust accuracy requirements they actually need. We often see people saying, well, I need 0.1 degree of precision in terms of my beam precision. On a low thrust system, it's often actually not necessary when you discuss with people who actually run the AOCS. And you need to be also aware of the limitation of the measurement systems on the ground. 0.1 degree precision on a plume for an electric propulsion system is usually not very realistic. And then, of course, in terms of operation, different technologies have can have limitation in terms of number of on-off cycles, which can be a very big constraints in some technologies. So on the flip side, we do not see that kind of limitation, but that's something to consider depending on your actual mission. Possibility to operate also at lower power. So instead of operating at the maximum power of the unit, operating at half the power might be interesting if you want to operate the payload and the propulsion system at the same time. And one last thing that is often ignored is that electric propulsion systems are high power system, and even with the best efficiency possible, you still will generate a lot of heat. And on a small spacecraft with small area to volume ratio, that can be a very big problem and limit your operation. So that's something to always very much consider. Then you have the integration aspect of the spacecraft. So traditional space, we have a lot of different modules that you would buy from different suppliers and integrate yourself. What we've been trying to do in a lot of new space companies and Impulsion, that's really what been one of the focus, is to sell the system as as an all-integrated system. So for example, what you see on the right here is the Impulsion Micro, where you have everything integrated into one box. So the tank is inside, the neutralization system, the electronics, and the idea is that you have 4 screws that you can just mount on a panel at the outside of the spacecraft. And that really reduces cost of integration, cost of like the engineering time required to design this into your system. And really is important in terms of use case. Another very important thing in terms of integration is, depending on technology, is the propellant choice. So the FIB technology that we use indium, which is a metal that is solid at room temperature. So it looks like lead, pretty much. It's a soft metal. Without toxicity or pressurized system. And depending on what propellant you have, depending if it's stored in high pressure, depending if it's potentially toxic in case of leakage, that kind of thing, that imposes a lot of constraints on the whole launch campaign and integration. It can be means for transport, you may need waivers. If you need to switch launchers at the last time, you might need to reapply for launch waivers, especially as a secondary payload. You might have safety requirements for integration facility and EGAC. You might have requirement on storage. And of course, health and environmental impact, which even if the system is certified, you still need to provide usually the paperwork to your launch provider or your internal quality audits. And one thing that is very often kind of swept under the rug for propulsion is the plume. So thrusters are not magic. They have to eject something to work. And especially for smaller companies, we do not have full simulation capabilities for the full spacecraft. Plume interaction for electric propulsion system are very complex. You have slow and fast particles, you have ions, you have neutrals, you have electrons going out. And this is something you really need to think about from the beginning of the design of the spacecraft. You can have risk of contamination with propellant. Even with gaseous propellant, you can have sputtering of material from your spacecraft that would redeposit on other parts of the spacecraft. You might have hot radiative elements. So this is something we strongly encourage you discuss with your propulsion provider. We try to usually hold a review meeting with the spacecraft designers to look at any problem that could be happening in terms of integration. And that's also valid for both in-flight configuration, but also on the ground. We had issues where people realized a bit late that they couldn't remove the protective caps on the thruster because the solar panels was folded on top before integration. So that's always something where suppliers will be happy to help and find solution with you. But this is something that really has to be considered when integration propulsion solution. So once you selected the right propulsion system for you, one of the very also important part is testing and QA aspects. In new space, there is really no standards in terms of what people want or what people do in terms of acceptance testing. And this is always something you can negotiate. I know at Impulsion we provide like different options in terms of packaging of what you get. Some people will insist of having a full TVAC with multiple cycles, and some people will only care about having one cycle at ambient atmosphere to just verify the workmanship. Vibration level, and also the possibility of having engineering qualification model that you can get to do integration also activities at your place. So that's something we provide at Impulsion, is both electronics engineering models, but also full thrusters engineering model that you can use for TVAC testing at your facility, for example, that kind of thing. And something that us engineers sometimes overlook also is the PA and QA aspect. Different companies have very different deliverable packages, and different customers have also very different requirements in terms of deliverables that they get with the thruster. So make sure that you have a good specification of what you get and what you want, because that can also block deliveries of systems sometimes. And this is also an aspect that takes time to generate. If you want to have a document that doesn't exist yet, it's not something you will get usually the next day. So really being clear on this is very important. And then operations. So that's something we're starting to have a lot of experience at Impulsion. One thing we have seen that very greatly help with integration is doing workshops with customers where they come to our facility and fire a real thruster with their flat sats. That can really iron out any bugs in terms of commission, operation, and all of these things. So that's something you could that really to consider, especially if it's the first time for you using propulsion system, to really speed up commissioning once you're in space. User manuals are the results of a lot of lessons learned. Especially across different cultures and different company philosophy and way of doing things, we have seen a very different ways of using user manuals. There is always possibility to optimize procedures for your specific system, but the user manual is usually a good base to base your procedures on, and also usually is result of a lot of lessons learned. And last point, righteous are busy times for everybody. So for example, you have, I think that was Transporter 4, where there was, I think, 4 or 6 spacecraft and a dozen thrusters on board. The earliest you know when you launch, and the earlier we can make arrangement for your help you with commissioning, the better it is for everybody there. I mean, we see on those transporter launch sometimes 40, 50 spacecraft, and it needs to, so it's a very busy time for everybody. So the earlier everybody can agree on what happens, the better it is. All right, I hope it was somewhat helpful for people who want to integrate propulsion. Of course, available for any questions.
Thank you very much, Steve. That was fantastic. Thank you for all that information about what your work there at Impulsion and what's been going on, the adaptations to the portfolio, the applications and things. That's great. So yeah, we've had a couple of questions. There was a question about the TRLs of the portfolio, essentially. That's
always an interesting question, right? Because in new space, TRL can mean a lot of different things. So the Impulsion Nano and the Impulsion Micro have been flying already. So they have demonstrated performances in orbit and matching very, very well what we had, the measurement we have on the ground. The Impulsion Nano R3 is not flying yet. It's in qualification as part of an ESA program. But we have clients that will fly it before qualification is finished. So that's also something that we have seen a lot, is that there is a lot of different risk-taking philosophy, and Since qualification, especially for electric propulsion system, takes a lot of time, including lifetime testing and that kind of thing. That might be more useful sometime to know what the qualification status is rather than a TRL number that is kind of arbitrary, right? If a product is not fully qualified, ESA qualified, but is already flying, what TRL it is.
Okay, great, thank you. Well, as you said, there's a bit of a different appetite for risk in new space, and you alluded to this actually in the discussion of how you go about integration and testing. You mentioned in particular there are no in this area there are no standards in new space for acceptance testing.
Mm-hmm.
Should there be?
Well, we see some commonality happening in terms of so a lot of people still are using NASA GEV's testing standards in terms of levels and things like that, which is a useful baseline. But there is a lot of differences between different technologies, and I think some technology where tests are more relevant for some of the tests are more relevant than others. So it would be nice if there was more standards, but I don't think that it will happen anytime soon. I mean, usually we try to provide like something we think is a good compromise, and then people will tailor on whatever risk they want to take. But it's usually a question of cost, and doing long burning of electronic, doing full TVAC for the full week of the system, for example, is a lot of cost that some people don't want to take on. Sure.
It's a balance of everything as it always is in space. So thank you very much. That's great. There's a couple of other questions for you in the Q&A function that you can answer via text. And please, to encourage you again, everyone in the audience, please do ask questions of any of our presenters today at any time. Next up, we have Marco from SteamJet Space Systems, please.
Thank you, Howell. So I will just share my screen. So I hope everybody can see the screen. So just keeping my own time to make sure I don't go over the 50 minutes. All right, so my name is Marco Pavan. I am CEO and co-founder of SteamJet Space Systems. What I would like to discuss today is a little bit about our technology, and then an introduction about the Steam Thruster family, so which products we have on the line, and a little bit of the use cases. So why do we actually need propulsion for your CubeSat or small satellites? And finally, I would like to spend a few words about our two main products, which are the Tunacan Thruster and the Thruster One. And the last one will be discussed in a collaboration that we are having with the Mohammed bin Rashid Space Center for the FI Demo 1 mission, which will be launched at the beginning of the next year. So first of all, a little bit about our technology. At SteamJet, we are developing an innovative water-based propulsion technology, which is designed mainly for CubeSats and for small satellites. Our technology is sustainable and safe. And this is because we use just low pressure water as the main propellant. And doing that, we can reduce the cost and the risks which are associated with other typical propulsion systems, such as high pressure cold gas thrusters or chemical systems which are using hydrogen or other chemical propellants. A little bit about our thruster family. So we have several products on the line. The first product that we developed, and it's also the smallest version of our systems, is the Tunacan Thruster. The Tunakan thruster has been actually launched in January with Virgin Orbit. We've been able to do some initial testing, but we're still waiting to do the proper, let's say, in-orbit testing in order to get some good flyer heritage on that. That is the smallest version that we have for our propulsion systems, and is designed mostly for CubeSats, which are in the order of 3 units up to 6 units. The Steam Thruster 1 is the one in the center of the slide. So what we can see is that the main difference compared to the Tunakan thruster is that we can use external water tanks on this system. So we use the same steam generation technology, but then we have external water tanks that we can customize according to the customer needs. So that allows us to carry as much water as we need for the mission. So this version is mostly designed for bigger CubeSats or small satellites over 6 units, and for small satellites up to 150 kilograms. And finally, we are developing attitude control thruster, which is still going to use our same technology, but it will be able to provide attitude control not just to small, but also to medium and large satellites as well. In terms of use cases, so why do we actually need propulsion? First, our thrusters can be easily integrated into any platform, and this is both from a mechanical and from an electrical point of view. So we made the system plug and play in a way so that it's quite easy to integrate in CubeSats and small satellites, and supports all the main propulsion needs. What we can see here is a typical these are basically the typical propulsion needs that you might have during your mission. Orbital maneuvers will give you the possibility to just change your orbit, perhaps to optimize the orbit depending on your payload. Constellation management, I think we all know what that is, and we heard discussing about that before. Basically, allows your satellites to be on the right spot in the orbit so that every satellite can communicate with the other satellites correctly during the mission. And you need an active propulsion system on board to do that. Otherwise, you will have to have separate launches, as we saw before. Collision avoidance, I think, is a really hot topic, which is coming up and becoming more and more essential. If you are on a collision orbit with another space object, and nowadays we have more and more space objects in space, well, then you need a propulsion system in order to basically change your orbit, either increase it or decrease it, in order to avoid that possible collision. So it is a very useful propulsion capability to have. And then we have deorbiting. That is, if we are deploying a satellite in a really high altitude orbit, over 600-700 kilometers. At that point, you're likely to be orbiting Earth for over 25 years, therefore violating the Re-entry International Guideline. So you need an active propulsion system which can bring you back to Earth and make sure your satellite doesn't stay for over 25 years in space. And finally, you might have the opposite problem. If you are, for instance, deployed on a low altitude orbit, 300-400 kilometers, perhaps because you have an optical payload and you want to have a really good resolution, then your mission lifetime will be pretty short, will be probably a few months. So you need an active propulsion system which can keep your satellite into space for a longer time. Now, I would like to talk about the Tunakan thruster. We can see in this video the Tunakan thruster installed on a typical 3-unit CubeSat. Our system is small, water-powered, sustainable, and it's able to provide quite a high thrust to the satellite. And what we can see here, and what we also notice on the video, is that the Tunakan thruster is one of the only systems that can be installed completely outside the main CubeSat structure. So we use what is called the Tunakan volume, which is available in CubeSat deployers, as we can see on the left part of this slide. So that is an extra volume which is usually used by a spring, which is then pushing the CubeSat into space. With this installation, we can basically install the Tunacan thruster outside the main CubeSat. That means that we can leave room inside the CubeSat for the most important things, which are the payloads and possibly other subsystems. And by using this approach, this particular shape of which is matching basically the Tunacan volume, then we can provide a very good solution, especially for small platforms, such as 2 units, even 1 unit, 3 units, up to 6 units. If we have a look at the Tunacan thruster, what we can see is that it is a fully contained unit. So this is everything you need basically to use your propulsion system, because there is the avionics on the top part, on the thruster head, where we have the heat exchanger, the electronics, and the control systems. And then there is a water tank on the bottom part. On this particular configuration, as we can see from the specs on the right, we can carry about 130 grams of water. And with a specific impulse of our technology, which is around 170, 172 seconds, that means that we can carry roughly 219 Newton seconds in terms of total impulse, just with this very small unit. And in terms of thrust and power consumption, we operate nominally around 20 watts. However, our system can work from 5 watts onward. Therefore, depending on the amount of power that we have available on the system, we can also customize the thrust. But nominally, we operate with the thrust of 6 millinewtons. And as I say, this could be slower or could be higher, lower or higher, depending on what is the amount of power that we have available on the satellite. In terms of applications, so what we can actually do with the Tunacan thruster, if we consider, for instance, a typical 3-unit CubeSat, which is around 5 kilograms, deployed at an initial orbit of 400 kilometers, well, we can see, obviously, if we have no propulsion, we have a quite short lifetime, around 1.6 years. And obviously, we don't have the possibility to do any orbital change, phasing, or collision avoidance. By bringing our propulsion system, so the Tunacan thruster, which again can be installed outside the main CubeSat structure, that we can extend the lifetime almost 3 times, and we can have an orbital change for up to 70 kilometers. We can also have orbit phasing capabilities, and most of all, collision avoidance capabilities. With a high thrust, it's a maneuver that can be done quite quickly. And finally, for a 6-unit, which is obviously twice as much as heavy, about 10 kilograms, then we have still a life extension. In this case, is about 2 times. We can have orbital change for about 35 kilometers, or we can have, again, the capability for orbit phasing and for collision avoidance. So I would like now to discuss a little bit about the Steam Thruster 1. And this, again, was in collaboration, basically, with the Mohammed bin Rashid Space Center for the FIDEM-1 mission. So the FIDEM mission is our payload hosting initiative, is designed to provide in-orbit testing to innovative payloads and subsystems. In this first mission, there will be our own SteamJet Thruster 1, and then another payload, this IoT communication payload, which uses 5G technology to forward and collect the data basically from remote areas. In terms of propulsion objectives for the mission, the main objective for us is to reduce the orbit from 600 kilometers to 500 kilometers, so about 100 kilometers orbit decrease. The initial orbit will be a 600 kilometers orbit, sun-synchronous, with an eclipse duration of about 35 minutes, which is quite long. And the main challenges that we faced during the design were definitely, well, a safe propellant was one of the driver. Obviously, we used water, so we didn't have any problem with that. A low power consumption was also a quite important driver for the propulsion system as well. The propulsion system has to deal with long eclipses, so that is another challenge that we had to face. And finally, we needed to provide high thrust, so in the order of the millinewton range. And finally, because of the payload, because the payload was a telecommunication payload, then the propulsion system should not generate any RF noise. If we have a look at the system that we provided, so this is, as we saw on the previous slide, this is a steam thruster one. We have a thruster head, which is the central part, and then we have the water tanks, which are located at the sides. In this case, we can also see how the propulsion system was installed in the satellite, with the thrust direction aligned with the Z-axis. So just to give a quick look about the specs, the overall system was less than 1.7 kilograms. The specific impulse of the technology is 172 seconds. So this allowed us to reach about 52.2 meter seconds. The overall size of the system was less than roughly around 2 units. And finally, we decided to operate with a power of 20 watts and with the thrust of about 6 millinewtons. And one of the limitations for us was the operational temperature, which for our system is between 5 to 50 degrees Celsius. So despite the long eclipse time, however, because as we noticed, as we saw before, was 35 minutes, just by using the satellite passive thermal control, we could keep temperatures above 0 degrees on the propulsion system without using any external heater. But the system itself, we developed the system in a way that we can also guarantee a minimum threshold by using the system's heater themselves. And obviously that requires a little bit of power from the main satellite, and that was agreed obviously with the customer. This can be customized depending basically on what is the power which is available. And also the integration of the water tanks can be done in a way that they can be located in a way where we can guarantee a higher temperature basically during the mission. So we can customize also from the integration point of view, the location of the system. Finally, in terms of the strategy, the propulsion strategy, typically you would do just a traditional Hohmann transfer to go from a 600 kilometers orbit to a 500 kilometers orbit. In this case, we had only 25 minutes per orbit that we could use. So we had to basically split the orbit in multiple firings. And we did that considering about 30 minutes that we could actually use after 12 minutes of warm-up. This allowed us to create about 0.2 meter seconds of delta V per orbit, which translates into roughly 244 orbits, or slightly more than 2 weeks, so 16.4 days. And this was thanks to a decent thrust that, despite the fact that we had quite a limited amount of time to use the system, allowed us to complete the full maneuver in slightly more than 2 weeks. So I am finished now. I think just 30 seconds over, but I'm happy to answer any question.
Thank you very much, Marco. That's great. It's very interesting data there that you shared with us on the mission. Yeah, it's in terms of questions, I think. Oh, sorry. So just had a question in on chat. What are the maneuver limits, such as momentum calculation of propellant during spaceflight?
So I guess is that related to sloshing, or is that related to?
Isan, is it possible for you to clarify? You can just do so in the chat.
I think I will. If you could, I think if who asked the question could perhaps clarify it, I would be happy to answer it on the chat. Okay,
no problem. In addition, then there are some questions on the Q&A. So we had somebody suggesting that 172 seconds ISP for resistor jet seems quite high. Can you talk about how you qualified this number?
Yeah, we did qualify that basically on the ground. Obviously, now we're waiting to have our data from the in-orbit demonstration that will allow us to basically double qualify that. We expect to have we expect to have basically a confirmation of what we already found, considering the deep vacuum of space. But we will share the data, of course, as soon as we will have it from our IOD.
Thank you. And there is a clarification on the previous question. So yeah, the questioner was asking about the maneuver limits. I believe that the maneuver limits refer to the water inside the tank.
Yeah, I think it's related perhaps to sloshing, so the water movement inside the tanks that perhaps could destabilize the spacecraft. So we do apply a small overpressure on the water tanks that provides a little bit more rigidity to the water, so which then is kind of forced to the walls. That is basically reducing the amount of sloshing. So we don't. Obviously, we're gonna have more tests as soon as this IOD with the Mohammed B. Rashid Space Center will go through. We'll have a lot more data that we can actually use. But by using extra pressure, we believe we will not have major problems with sloshing.
Excellent, thank you. There's a couple of questions for you in Q&A, which I think would be better answered via text because they're a little bit more technical. But I just had a question just from more generic industry point of view. Was obviously you're based in a different country to the Mohammed Rashid Center. So how did you go about working together, especially over the last couple of years?
Well, actually, we met in one of the networking events, and then eventually there was they were looking for innovative payloads to provide these in-orbit demonstrations, similar to other initiatives that we have in other countries at the end. And as the Mohammed B. Rashid Space Center was looking for international collaboration, I think just ended up to be, a very good occasion for both of us.
Right, fantastic. So, yeah, well, good. Best of luck with the rest of the mission. Thank you very much for sharing the insights there today. Everybody will be glad to know I've got nothing else to pitch for you guys between these two talks, so we can move straight on to hear from Bradford Space, please.
Yes, let me share the screen here and see if it works. Okay, is that working?
Yes, perfect, thank you.
Okay, thank you all for listening in. My name is Willem Dingertz. I'm the thruster lead at Bradford ECAPS. And
Peter Thornallen, I'm a propellant lead.
So we will start this presentation with a brief introduction of the Bradford Space Group, ECAPS, and our high-performance green propulsion, or HPGP technology, including propellant, thrusters, and propulsion systems. But the main focus in this webinar is the in-orbit use of mainly the 1 Newton thruster. So Bradford Space Group, which ECAPS is a part of, is a trusted supplier of everything from sun sensors, microgravity glove boxes for the ISS, to reaction wheels and green propulsion systems. And we have over 2,000 products in space. The group has facilities in the US, Netherlands, Luxembourg, and Sweden. And ECAPS are based in Solna, Sweden. It's a suburb of Stockholm. So the high-performance green propulsion thrusters, which this webinar is focusing on, are scalable from 100 millinewton up to 200 Newton and higher. The technology enables high thrust, impulse, and delta V capability for spacecraft ranging from CubeSats to satellites larger than 1,000 kilos, anywhere from LEO to GEO and deep space. And the use cases include orbit changes, station keeping, constellation phase management, collision avoidance, and deorbit. For example, the Planet Skybox satellites lowered the entire fleet of the skyboxes from one altitude to another because customers were requesting higher resolution imagery.
Yeah, we also have our own propellant. It's different from hydrazine because it's made from an energetic salt and some liquid components. So this makes it different because whenever there's a mishap, a leak, or let's say that the thruster is operating in the wrong way, the propellant, if not combusted, it will be exposed to the vacuum of space, and the liquid components evaporates and leave behind the energetic salt. And that could create problem because this is like a solid propellant left behind. Yeah. Otherwise, our propulsion modules, they are very much like a monoprop hydrazine system. Tanks, tubing, valves, all of that is COTS components for hydrazine systems. What is different is the thrusters and the propellant. Otherwise, it's very much the same. However, there are some differences in how this is operated. Yes. Yeah, and we have also now a lot of experience from launching our products into space. We have 25 satellites, more than 100 thrusters in orbit, launched by different vehicles in different ways, in different satellites. And Willem will now talk about the experience of operating them in space.
Yeah, so moving on now to the operational part of this webinar. We want to provide a short but insightful perspective on how to operate HPGP thrusters. In this slide, you have the typical life cycle from purchase order to a receipt of thrusters, to propulsion system integration and testing, and finally launch and in-space operations. And if there was only one advice that you bring with you from today, it's that the user manual should be opened up at the same time as you start designing your system, and carry it with you throughout the entire lifetime. And also that all operations are done according to the manual and within the limits defined by the product specification. And these advice that are within the manual or advice and guidelines, they are based on the experiences of the operation of 100 plus HPGP thrusters now in space. So I will jump right into the propulsion system considerations, where the propulsion system provider have to consider construction materials, let's say tubings, tanks, etc. And to fluid interface, ECAPS prefers that the thrusters are welded to the propulsion system. Which pressurant to use? We have lots of experience using helium as a system pressurant, and temperature control has been mentioned several times today. Is also a very important factor, both for the propulsion system and for the satellite operator to consider. The propellant LMP103S has undergone extensive material compatibility testing, and it's compatible with typical COTS propulsion components. And with ground testing, we have demonstrated more than 15 years of storability in our propulsion system setup. And once the thrusters have been integrated to the customer's propulsion systems, typically undergo additional testing. I mean, we do the acceptance testing at ECAPS and deliver the thrusters, but on the propulsion system level, they are typically tested again. Here it's important to consider the interface between the thrusters and the propulsion system, and the design of the brackets, so that vibration levels that the propulsion system or the satellite experiences are not amplified throughout the structure, so that the vibration loads input at the thruster mounting interface are so that they are within specification. Otherwise, for electrical checkouts, leak checks, care must be taken when performing these operations. Once the satellite or the propulsion system has been integrated in the satellite and made it to the launch site, ECAPs typically assist with the propellant loading campaign. It's important that the propulsion system and satellite, again, are designed in such a way that service valves, for example, are easily accessible for the propellant loading crew. Otherwise, it will create some headaches. And also enable operations to comply with range safety requirements. Typically here, it's ECAPs are happy to assist with customers on this topic. Additionally, once we are integrated in the rocket, the hardware is once again exposed to vibration and shock environment. So it's important that the structures are designed in order not to amplify loads. And now finally, we have made it into space with our products, and we are ready to operate the thrusters. The first thing that has to be performed is the commissioning of the propulsion system. It includes extended preheating period of the thrusters, venting of the blanking gas between the propulsion system latch valve and the thruster flow control valves. Finally, opening the latch valve. So you prime the system, you fill propellant throughout the tubing up until the thruster flow control valve, and while still maintaining the preheating. And then you can perform initial firings to fill the thruster valves with propellant. And after that, you're ready to go. So the thrusters are nominally operated within a voltage range of 24 to 32 volts. ECAPS recommends the regulated bus at 28 voltage, or 28 volts, but typically the unregulated bus is very common. Depending on the bus, we have seen operation at under voltage or over voltage, and this has an impact, especially the under voltage. It will affect the preheating time and the time it takes for the thruster to reach the operational temperature, and it can also result in a lower preheating temperature if the voltage is far too low, so that you do not reach the required temperature to start the thruster. A lower voltage also means a lower pull-in force on the flow control valve. Operating at an over voltage risks shortening the lifetime of the electrical components of the thruster. I mentioned now a couple of times preheating, but for those of you who are not familiar with HPGP thrusters, they must be preheated to a set temperature prior to firing in order to facilitate combustion. So the thrusters, unlike hydrogen thrusters, cannot be cold started. Most hydrogen thrusters have a limited number of cold starts that they can do. Otherwise, they're also typically preheated. So prior to opening the valve, the thrusters must have been preheated to roughly 375 degrees. This takes typically 12 minutes with the integrated heaters, but then they must also soak at this temperature for an additional 18 minutes in order to compensate for thermal lag between the temperature inside the reactor and where the temperature is measured. It is possible to perform emergency preheating, but it's not recommended, but that can allow for unplanned collision avoidance, for example. Cold fire, yes. If you, I'll get into the cold fire later, but if you start open the flow control valves at the too cold temperature, that is what the cold fire is. Like Peter mentioned, the solvents of the propellant will evaporate and leave pure ADN behind, and which is an energetic salt. And if you heat this again, when you have a reactor full of ADN salt, you have created a quite bad situation. But if you, it is recoverable if it's identified prior to performing preheating again. Coming back into how to successfully operate the thrusters, there are some requirements placed on the satellite control system, including such things as preheating control, so that you have the correct voltage and reach the correct temperature and regulate at this temperature for for a total time of 30 minutes. And we recommend that every thruster can be controlled individually, so that you typically a satellite has maybe 4, 8, or 12 thrusters, and they should all be able to operate independently and not in groups. So once you operate, or once you want to use the thrusters, the flow control valve also needs to incorporate an electronics box that allows a hold voltage, so typically way lower than the bus voltage, around 10 volts. After that, you have opened the valve and you keep it open, it needs to go down to the hold voltage, otherwise there is a risk of overheating of the valve. For the thermocouples that are incorporated in the thruster, which are used to measure the temperature, we recommend using differential inputs to read the thermocouple input to reduce grounding noise, which may otherwise interfere with the signal and provide incorrect temperature outputs. Again, this is with the risk of performing a firing at a wrong preheating temperature, for example. Additionally, the system also needs several firing inhibit controls, such as over temperature, which could be both preheating above the set point, or if the entire propulsion module were reaching non-nominal temperatures or under temperature. We have also you should not be able to open the valve if the thruster thermocouple measurement is below the requirement, and also if you have too cold or too hot propellant. And for this last part of the presentation, we'd like to focus a little bit more on the cold fire and how to recover from this. So it's a potentially catastrophic event there's a big risk of damaging the hardware if it's done. It's typically a result of either a faulty command, control system error, or a hardware error, like the thermocouple misread. And like I mentioned, when the propellant flows into the cold reactor, all the solvents will evaporate, and you leave behind the ADN, the highly energetic salt. And if you once after this perform another preheating, this energetic salt will there's a risk of a rapid gas evolution, and that can damage the hardware. However, together with a customer, we have demonstrated in orbit now that there is a solution to this.
Yeah, thank you. Next slide. Yeah, we did study how to recover, how to decompose the ADN in a controlled manner instead of having an instant ignition. If the cold firing happens at ambient room temperature, so to say, and is then immediately set at the preheating temperature of 375 Celsius, there is going to be an instant ignition of all the ADN at around 130, 140 degrees C. And all of the gases developed within the thrust chamber will just break things. So this is a procedure where we gradually heat the ADN to have a controlled decomposition. You can see the duration here of each temperature step. It is in number of orbits in LEO, which are about 90 minutes each. So we start with a preheating to verify regulation on the thruster, and that means that if you're going to be able to do this, you need to be able to control the set point of the preheating temperature, and it needs to be fairly stable also, so it doesn't swing wildly between different levels. So in order to verify that it works, around 90 degrees C is a good point to start to see that the regulation works. Then the temperature is increased to 110 degrees C, where the ADN melts. Takes a couple of orbits to be sure about it. If there's any solid ADN remaining in the thruster, it could block the exit, the exhaust, and then you can still have a pressure buildup. The preheating is then done to get it up to the temperature where the decomposition starts. So We park it at 135 there for one orbit. And then there is a set of steps here in temperature, 140, 45, 50, etc., up to 180 degrees C. Several orbits on each level. And at this point, most of the ADN has gradually been decomposed into much more stable products. And by doing the last steps at 190 and 200 Celsius, all the remaining decomposition products are removed. And finally, the nominal preheating temperature can be reset again. And after this testing, the thruster is actually operational again. We need now, however, to say that this has only been tested, verified in orbit. We haven't done any of this yet on ground. Because we haven't really verified this under controlled conditions, we will not assume any liability if you use this procedure. But we recommend you to talk to us if you experience this problem. This should work, but at this point we can't really put any guarantees on it.
Thank you.
Thank you.
Great, thank you very much, guys. That was really interesting. Yeah, nice to see examples from the launch log there, and the looking at the entire life cycle of what is really required to develop, integrate, and use the thruster was really fascinating. So thank you. In terms of questions, I do have one to start this off with. You spent obviously some of the time there talking about all the different aspects of testing that goes into the integration of a thruster, and there are several elements to this, as you shared in the life cycle. What have you found are the common sort of misconceptions or underestimates from a satellite integrator when it comes to testing?
Power. I would say under voltage is an issue I've seen. The underestimation of the power budget on the satellite, especially, and also some concerns on dynamic analysis maybe not having been done.
Right, interesting. So
we can also add to that you need to be able to operate your propulsion module on ground in a way that you can also check all the leaks of different components. So you need to be able to operate thrusters, latch valves, and pressure transducers and temperature sensors. Otherwise, it's very difficult to perform leak testing and do the loading of the spacecraft, for instance.
So the challenge there to carry out that testing, is there more around having an adequate facility, or is it about the electronic and computer system control that you would need to build to operate the thruster for the tests, or both?
It's both, but it is. I mean, a hydrogen system, you're not allowed to keep the system up and running while you do the loading with hydrogen, because there's a very high risk of having a fire. Hydrogen is very flammable. That is not a problem for us. So normally the launch site allows us to run the onboard computer, but it needs then to be programmed in a way that you can, in a controlled way, operate component by component for the test sequence. If you're not having the system run by the computer, you need to have separate electronics, which from the outside, using connectors, can operate valves and all the systems on board. Right.
Okay. Yeah. So it is quite a challenge for integrators.
Yeah.
Interesting. That wraps up all of our major presentations today. So yeah, we'd just like to thank everybody for spending time with us. I can, if there are any other questions that anybody has, I'll just give a brief overview of what we heard today. So there'll be time for those questions to come in and to be answered by the presenters. But yeah, we heard from Mael at Exotrail. He described the portfolio of the company and gave details of the 2020 IOD mission. This was really interesting to see the whole timeline of the mission, which just shows the challenges that can occur with bringing new innovations into space, which I'm sure everybody in the audience appreciates, and all the presenters certainly do. And then discussing the use cases of constellation deployment and comparing rideshare versus dedicated launches. It's very interesting. And then we heard from Lou at Impulsion. He explained the evolution of Impulsion's portfolio and the orbits in which the different systems fly. He also shared with us data on deployment and formation control, which was interesting to see that data. He also discussed how to best share requirements for a use case as opposed to a technology, which is really clear. I think that's something we're seeing in lots of areas in the industry. We're moving on a bit from the idea of talking about technologies and innovations to talking about use cases and business cases and results and end users. And I think that's signs that the industry as a whole is maturing and points to a lot of positive signs for all the presenters here today. And I think they've shared with you how their own heritage stands them in good stead with these new opportunities of the future. Lou also discussed performance requirements for small sats and how these maybe can differ from large systems, and then how to integrate systems. Then we heard from Marco at SteamJet, who gave an overview of the use cases that they have looked at and that their systems are suitable for, and a detailed presentation of SteamJet's products, explaining what sort of missions and maneuvers they are best suited for, and also share with us a variety of really interesting mission data on operations and thermal control and propulsion strategy. I think talking about the timings, the sort of maneuvers, how they work, how the operations how they handle thermal control, and it's very clear to see that there's a lot that goes into this topic, and I think that was again something that was emphasized by all the speakers today. And then finally, it's great to hear from Bradford Space, obviously a very strong heritage in space, and the introduction to their technology, sharing the launch log is just illustrative of the approach that companies like this have to take to the industry and the opportunities that are out there for using the technologies in different ways and across different missions, which is great. And then in-depth information on the product lifecycle, as we've just discussed, including testing, launch, and in-space operations. And the answers to the questions, I think, further illustrate how much goes into this and the importance of relationships between satellite integrators and subsystem providers and everybody else really involved in the missions. As was mentioned, open that user manual early on and be prepared to adjust what you're doing. So that's fantastic. And then it's specifically the process of dealing with a cold fire event and what can be done there, obviously with the proviso that this is something that's been tested only initially in orbit. So it was great to get all those insights from everybody as well. So thank you to everybody. I think we had a very good session. Just to share a little bit about our own work at Satsearch. We have been working on developing the global marketplace for space for a number of years, and we are now providing access to thousands of products and services from suppliers all over the world. We've got a large number of suppliers in a lot of different countries and territories, and we're helping people who have to carry out trade studies or other procurement processes, helping them to find the information that they need, making it, providing access to it, and trying to give them access to it in a way that suits them. We carry out events like this in order to help educate the market and help position the companies that you've heard from today, in order for people in the audience to really understand what possibilities are out there in the industry. If anybody in the audience does require help with any trade studies or procurement purposes, we would love to facilitate your requests via Satsearch and help you find what you need in the industry, or just discuss what your requirements might be, as I'm sure all of our presenters would as well today. All of the request system on Satsearch, by the way, is free, and we would be more than happy to hear from you across any of our channels. Also, if you are a space supplier out there in the audience today, then we would like to invite you to come and get listed on Satsearch as well, and we can expose your own products and services to the global marketplace. And then finally, in order to hear a little bit more about our work, we're across a number of channels and in a number of different content formats, but the three that we think are most relevant today are: we run a podcast where we discuss the topics similar to what we've heard about today. Some of the guests that we've spoken to today have been on the podcast, the companies, and we share information about the market, try and get to the stories behind the sort of headlines that you might hear elsewhere in the industry and mission announcements. So we would love, the podcast is available on all major streaming platforms, and also you can find it on our blog too. We also have a weekly newsletter in which we share trending stories about the industry and updates from our own work and the work of our members, such as the missions and news stories and updates that you have heard today, and other information in the newsletter as well. And then finally, there's our Slack channel where we kind of discuss all of these things in real time, and we would be more than happy to welcome you to that and to have you in our little corner of the internet. So once again, would like to thank everybody for attending today, but in particular would like to thank all of our presenters. I think you all did a fantastic job, and we are very, very grateful for hearing all those insights from the industry and the industry stories today.